the organizers to allow me to talk about this nice conference. That's been very exciting. I'm talking about cosmological divide, separating the expansion from collapse. This has been based on work. It's based on work done with a few collaborators, mainly Mocon Review, who's now in São Paulo, Felipe Mena, who's from the University of Minho in Portugal, and then a few Brazilian guys, Alan Maciel, Elcio Abdallah, Daniel Guarin, and Pedro with whom I did the last two works. So, what's the main idea behind this work? So everybody is well aware that at large scale the universe is expanding, and yet we have a plethora of bound structures within it. It's obvious our idea is that these structures grow from perturbations to charge superimposed on the background expansion, and this happens in a way, in such a way that nowadays local physics is very much immune to the global physics, and in fact most of the objects that we see in the universe are visualized from bound structures. The only ones, the threshold in a way, is at the scale of superclusters of galaxies, so scales from 30 megaparsecs and beyond, which we know are not yet forming bound structures. So, so the idea of this work is to try to look at general relativistic criteria to separate expansion from collapse, and the dangers of these tasks are not difficult. So this is based on 5 publications that we've done till now. And I start very early, in the beginning of GR, reminding us that spherical models are among us since the very beginning, very inception of the GR. The first solution dates from 96, from 100 years ago, precisely. And basically, spherical symmetric models have been mostly studied in two separate or alternative fashions, either looking at the expansion of the universe, which dates back from models of Friedman and Tolman, or looking at the contraction in order to explain the formation of collapse and bound objects. The later avenue has started with Lemaitre first, and Tolman, Bondi, Schindler as well, and many others. So, I'm repeating myself, but our aim here is within GR to study the separation of these two regimes, or the interplay between them in a way. And this is a purpose which has been considered previously in literature in different fashions. I mean, Bondi looked at Newtonian models in the 60s, looking at the criteria to have balanced spheres, uniform spheres. Warner looked at the collapse of open models, for instance. In the 80s, Barrow, Galloway, and Tipler looked at the recollapse conjecture within cosmological models, so you know that closed models may recollapse, and so they looked at criteria to separate those which do from those which don't. Carr and Kohler looked at self-similar collapse, and also related to the Galois-Stork, which is the interplay between local and global physics. We have very distinguished people here, Einstein and Strauss with the Swiss cheese model that you know well. George Ellis looked several occasions at this interplay between the local and global physics. Valerio Faraoni with Jacques did the same more recently. And within the study of spherical models and collapse in the 30s, there is a central result, which was derived by Oppenheimer and Volkoff, who looked at collapse spherical configurations, and in particular looked at conditions for equilibrium within GR spherical stars, static stars, and they obtained the well-known this well-known equation, which became known as the top equation, Tolman-Oppenheimer-Volkoff, which tells you that you have to have a sufficiently negative gradient to be able to withhold the collapse, to have a static configuration. I'd like to point out that you have three ingredients here which are not present in Newtonian mechanics. One of them is the coverage of a space-time, which is encapsulated in this 1 minus 2m over r term, which in a way weights this derivative, this radial derivative. You have the relativistic inertial mass, which is this one, and you have, in a way, the relativistic gravitational mass, which is this factor. Also deserving to be emphasized or singled out is this model of spherical collapse of Gunn and Gott, which afterwards has been thoroughly explored by many, including many of the presents. Now, after this, I've got a small list of publications here related also to the Swiss cheese model. Pierre has worked on this as well. And there is a nice review by Mark Mars and Friedman and João Vera, which I recommend. Now, related to our work, there are some results which are not very well known by Luis Herrera and Ángela Bispo Herrera Varela, who have looked at something they call correcting of stars, and this is very much related to what we will do. So they consider perturbations of static configurations in stars, and they find that if they have anisotropic perturbations and within anisotropic fluids, then they will have a cracking situation. If the fluid is perfect and there are no anisotropic perturbations, they are isotropic rather than anisotropic, then they don't have cracking. Now, after Carson referred the danger of having enemies around, I have here a list of some of the present people who have worked in very much related to the subject, and I apologize to all the others who have done as well, which I couldn't put here. We consider a metric Tolman-Volkoff model, or a spherical inhomogeneous model. To remind you, the typical LTB, the original LTB model, can be written in this way. this corresponds to geodesic motion of matter particles, of matter content, and so you have this moving time. And I wrote this with dependence on this factor here, which represents the energy of the configuration, the initial energy or energy conditions. So in a way, E is the sum of the potential and the kinetic energy of the distribution of particles within the model. And the field equations reduced to these two. Basically, this is the Hamiltonian constraint. And here, in this case, or in the case of Tolman's solution, which pertains to dust, so to pressureless matter, there is the mass of each shell is independent of the mass of the others. And here I consider the cosmological term just for completeness. And also the energy factor or parameter is also just dependent on the radial coordinate, which is not the radial area. Okay? In this case, just the radial. You have a second derivative here, and this is very much Newton's central force. So the solutions are well known since the 30s. You've got these conformal time definition here, and you've got the solutions for the three possible cases in terms of the choice of parameter of the initial velocity. So you have here you have elliptic models. Here you have parabolic models, and here you have a flat model. And I'd like just to notice that here you have a constant of integration for each of the shells, because the motion of each of the shells is independent of all the others, which depends on the shell. So it is not necessary to have a cosmic Big Bang, a coincidence between these initial times for each of the shells. And in fact, Martino-Elsevier has, for instance, suggested that inflation, or at least the homogeneity of the universe, could be explained by a delayed Big Bang time. So this is something which is not really Now, what is our aim? Our aim is to look at these shells and to try to figure out beyond which shell you have just expansion, or at least, and so the two conditions are very simple. They are conditions of stationarity in a way. One of them is you want to have a turning point, so you have to have a vanishing radial velocity, and on the other hand, you would like to guarantee that you at that shell you trade contraction into expansion. So if you look at the pure Tolman-Volkoff model with pressureless matter, that is not possible because this is negative, so all the shells will be collapsing in spite of their initial. Okay, so if you consider lambda, you realize that with lambda that is possible. Then you have a possible threshold, because then you can associate a vanishing also of the acceleration for a certain shell which satisfies the vanishing of this right-hand side. Now, to work in a proper way, the best is to adopt 1+3 splitting, and in this case we followed a formalism which was developed by Lasky and Lumen at Monash University in Australia, where they started with Pellet vehicles and coordinates and expanded, generalized their formalism to separate, started to get the ADM splitting. And so we work in this case with a lapse function and the shift. And so this allows for acceleration. And the advantage of these kinds of coordinates is that you don't have to, you avoid having to impose matching conditions in spheres if you want to have kind of different behavior on different sides of the same sphere. So, so with these variables, the vanishing of the radial velocity, so the stationarity condition and turning point, becomes simply this, which means that you have a combination of the shear and of the expansion of the shells vanishing, which in this case, in the simple case of a perfect fluid, is going to impose the same condition that we had earlier on, which means that the energy must be minus 2m over r. And if you impose the vanishing of the acceleration, in this case, there is a typo here, this should be a plus sign. You get basically the vanishing of this quantity here, and so you realize that which is not surprising actually, the vanishing of the acceleration reduces to the Tov equation to be satisfied at the shell that you are considering. So the difference with the traditional way of using the Tov equation is very simple. The Tov equation is almost kind of an equation of state to be satisfied by a star or by a spherical configuration which is in static equilibrium. And in this case, it's just a function which vanishes at a given radius. By the same token, you get, in this case, you get a vanishing, this is the expression with lambda present, so it's more general. You get the vanishing of the time dependence of the mass. So in a way, there is also a possibility of having a kind of trapping surface at test shell. You can also see, and this is interesting, that the vanishing of the radial velocity and the acceleration, but in particular the turning point condition, imposes that the three curvatures should be positive. Okay? And so this does not contradict, obviously, the fact that Borner had studied recollapsing models with negative energy or with which were hyperbolic, I mean, with positive E parameter, because the sign of E does not fix the curvature.
So is it still in the usual LTD coordinates, or is it from a very strong coordinates?
This is a mix.
Okay.
I'm going to show you the dictionary. Okay. So it is possible to make a dictionary transferring the Convey coordinates and of Gauge invariant 1+3 formalism to the traditional E and M values. Okay. So this is perhaps a more faithful representation of what we are dealing with. We are dealing with two conditions, and one of those conditions is the condition of stationarity, that is a turning point of the shell that we are considering. The other one is the condition which established the vanishing of the acceleration. So in general, the surface which divides expansion, or locally divides expansion from contraction, lies in between. Okay? And so these two tend to the other one, and they coincide at time infinity. Now, a very simple illustration of the possibility of having this is figure one, is obviously if you consider a cosmological constant within a burst model, so lambda CTM satisfies these two conditions at a given shell. It all depends on the choice or distribution of energies, of initial energies along R. Okay, but at least you have one scale, and this is known since most 100 years ago, that lambda imposes a scale of close to. Now, if we are really doing with cosmology, or cosmological models as the underlying setting, we should consider anisotropic stresses, because isotropic stresses are more naturally fulfilled when you are under equilibrium, and obviously, because cosmology is really a non-equilibrium system. So, so in this case, we have to consider an energy momentum tensor which has all the possible components. So these are the usual two terms of the perfect fluid. to which we have to add an isotropic stress and possibly a heat flux. And in the first approach, we just dealt with the anisotropic stress. So, so here you see within the Planck-Wurst formalism, we have the linear derivative along the flow of the radial area, and this is the traditional form of a mathematical model with the E parameter and the mass parameter. Here we have the pressure and the anisotropic stress, and this alpha, which is the shift function or the logarithm gradient of the shift function, basically is the gradient of pressure. Okay? So it is possible to translate, obviously, our two conditions here, the stationarity condition and the equilibrium condition, which generalizes, in this case, the Tolman-Oppenheimer-Volkoff equation to the case where we have isotropic stresses. And the dictionary I was telling you about is basically here. So you can see that the logarithmic derivative in time of R, which normally people associate with the whole flow, so R dot over R, in fact is not R dot over, is not the Hubble flow, because the Hubble factor is theta, this is the expansion, and what we have is a combination of the expansion and of the shear. So in general, unless we are under a particular setting, we won't have a shear-free expansion, and so in this case, we have to deal with gradients at the velocity. So you see here the equations written in the usual way, involving the expansion of the shear. Okay? In a spherically symmetric model, all the quantities are share the same eigenvalue vectors, and so we can just deal with scalars to represent the expansion, the shear, the Hessian of the shift, and the electric part of the tensor, the anisotropic stress. So all of them are parallel in a way. And we have constraint equations which are here, and the propagation equations here. So this is the equations that you've seen time and time again here in the previous talks. Here I've got a comparison of the two formulas. This is what shows you how things go. So here, this is the usual way you find in cosmology, where you have the generalized Friedmann equation. Here you have the equation when you introduce the IBM mass, or Misner-Sharp mass, and the parameter here, E. And so, in a way, this description involves a non-local representation, since you are the ADM mass is the integral of density and of the along R. Okay. So, coming back to this illustration, so this illustrates something which is, in this case, in an astrophysical setting, but this is basically what can illustrate also the cosmological model of these conditions. Herrera and collaborators defined the quantity R, which basically is the acceleration. And so, sorry, the deceleration actually. And so, what they find with anisotropic stresses is that when they perturb, they are changes from contraction here into expansion there. So, and so they found this provides an illustration, in this case astrophysical, of this criteria to have a separating shell. Sussman and Pavon have worked on the model, a particular model where they have dust and radiation. It's a particular model in the sense that it is geodesic, it falls geodesically. And when we look at this model to illustrate our results, the two separating conditions, we find something which is curious but not really strange, which is that the part of radiation must have be negative, so it contributes a negative energy density, and so sorry. it is possible also to find conditions. These are local conditions, so you can derive results such as realizing that if you have a shell where the expansion vanishes, then it will vanish at other shells in between a given radius and another one. So it's possible to derive multiple results. We looked at shell crossing in a very naive way and realized that you can, if you allow that the shells interpenetrate, so they cross each other, but they don't change masses, then you are able to show that you will form in a cosmological context. You have let's see, yes, you'll have innermost shell and an outermost shell, and so and this obviously is just depending on your choice of the distribution of the energies. Okay, so I'll finish. So conclusions. So the conclusions that I want just to stress are simple. It is possible to have local conditions, but global conditions is a lot more difficult for separating expansion from contraction. Basically, what you require is that the generalized Rayshard equation be vanishing. So, in a way, you are violating the strong energy condition when you are doing so. And so this recovers basically the same results, or results which are compatible to all of those that we have been considering in cosmology in the last 20 years when we look at inflation. So in a way, the expansion of the universe is the inflationary part of a model which is spherically symmetric, while the contraction part is the part which satisfies the conditions that we usually associate to matter, although all of the energy conditions, as you know, are violated in one or another context. So this is basically it. I just have another conclusion, which is, and this is, I think you will agree with me, that treating something which is a divide is the only part which is the importance. So thank you for listening.
Questions? Earlier on you mentioned a certain figure, I forget exactly what it was, for the size of the shell. Does this fit in with that?
For the size of the shell,
I
mean, the figure I expressed is that you know that superclusters, which are 30 megaparsec wide, at least, are not visualized. So if they're not visualized, they are good. They provide a kind of a rough idea of what the scale, the minimum scale, should be for you to have this kind of threshold between contraction and expansion.
Actually, like these people in Hawaii, tourists, found this Laniakea supercluster. They did this by looking at velocity field and arguing Laniakea has a boundary, which is a divide between one supercluster and another supercluster. It's clear that it has not virialized yet, but still, you can perfectly well define this boundary. It's like looking for the watershed. Where does the water will go within a mountain? So in principle, you could do exactly the same thing here. Rather than looking at density, you would look at velocities.
Yeah.
Those are the ones that are going to tell you whether you're going to collapse to a given region before you realize. Collapse to a given region or to a different one. So can you implement that with your formulas?
Well, I think you can do it probably with numerical tools.
Because in this case that they find, they're not 30 megapascal, they're 80 megapascal in radius.
Yeah,
so 100%.
See, if my understanding is correct, this is exactly what you were doing, using because you divide the while the divide area is defined in terms of the expansion, the local expansion rate, theta, so it is exactly using velocities that the divide is made.
But
not
I
using
mean,
density.
if you want to contrast models, because here you don't have a specific equation of state for distribution of matter. Obviously, in the case that you are considering, the distribution should be very much along the CDM or something like that. I don't know.
Also, I don't think you use the peculiar velocities, because in that kind of phenomenon, you have to balance the peculiar velocity with the expansion.
That's right.
I don't think you have
Tracking expansion.
That would presumably could be used as initial conditions for the parameter E, the energy. I mean, you could look at to take that scale as initial conditions to see how they would evolve for scales larger and smaller. But
how do you define peculiar velocity?
No,
Before you
no.
have the idea of the separation. Can you speak up?
Well, there are ways we should introduce relativistically peculiar velocity, but then you already have pretty tough equations, I guess, with that.
the full system.
The other problem is that the MTB, you are in a catch coordinates in which you are essentially the center of the whole thing, right? And that's going to be a problem when you want to match with observations, because then you have to factor out boost. And that's, that probably contains enough error to just shift your surface in a way
But
that
actually, we're not that far from the center of the little void which separates Laniakea from the Pesach distance.
okay, so in that case,
Again, so when you're working in 3+1 formalism like this, and you have, so when you define the expansion scalar, the local expansion, this is completely coordinate independent.
yeah.
So this is irrespective of the split between the background and peculiar velocities. This is something which is completely observer and.
But the collapse, the motion, the collapse
Yeah,
is
collapse
peculiar,
itself.
whereas the expansion
Yes,
is two different
yes.
phenomena.
Depends on what they are observing.
No, but if I may, on top of the LTE collapse, you can of course do your perturbation theory and deduce the peculiar velocity of say galaxies within the plus time, which is itself collapse.
Yes,
That's
yeah,
the
again,
problem.
but you have to add another piece to the
Sure.
model. That's the one.
Obviously, the ultimate goal of this kind of work is to define typical sizes for cell universes, like Timothy does, things like that. And, so, from a spherical model, you just get a rough idea of what are the criterion that you should explore. This is in a very much like dynamical systems, where you have stationarity conditions and then you study perturbation. Well, you study, depending on your system, the stability of your critical points, and then with the difference, which is that this is basically Navier-Stokes equation. The acceleration is Navier-Stokes equation when you have all the terms there with the anisotropic stresses. So it's immensely difficult. You can do it in, for instance, for shear free models.
Maybe a last. Is there any last comment or question? You should move on. Thank you.